You know, inside every single piece of electronics you own, your phone, your laptop, everything, there's this secret, high-speed race happening billions of times a second. It's this frantic race against time, and if the wrong signal wins, well, it can lead to total chaos. So let's dive in and figure out what is really going on here. And this, right here, is a real question someone asked, trying to wrap their head around digital circuits. It's the perfect question, really. It's the central mystery we're going to solve today, because the answer is absolutely fundamental to how all of our modern tech works. All right, first things first. We have to define the problem. What are we even talking about when we say race condition? It sounds pretty dramatic, right? Well, in the world of electronics, trust me, it is. Okay, imagine two runners sprinting for the same finish line. In a real race, we just want to see who wins. But in a digital circuit, we need the outcome to be exactly the same, every single time. A race condition means the result is basically left up to chance, all depending on these tiny, unpredictable variations in speed and timing. And that's the absolute last thing you want inside a computer. So here's the bottom line. The entire goal of digital design is to build systems that are predictable and stable. A race condition just throws a wrench in the whole thing, creating randomness and chaos. We want our devices to be reliable, dependable workhorses, not some kind of digital slot machine where the output is always a gamble. So to understand where this crazy race happens, we've got to meet the main character in our little story. It's the most basic, most fundamental piece of memory in the entire digital universe, the flip-flop. Think about this. Every single piece of data on your computer, every letter in an email, every pixel in a photo, it's all stored in millions, sometimes billions of these tiny little memory cells. They are literally the microscopic bedrock of our digital age. This here is the simplest version, the SR flip-flop. It's got two inputs, S for set, which tells it to store a 1, and R for reset, which tells it to store a 0. Seems simple enough, right? Well, not quite. Now we get to dig a little deeper. Because even this incredibly simple circuit has a hidden vulnerability, a critical weakness that gives us our very first clue in this whole mystery. This is what it looks like on the inside, built with just two simple logic gates. And see how the output of each gate feeds back into the input of the other one? This clever little loop, this cross-coupling, is what lets the circuit remember its state, to hold on to that 1 or 0. And this table is basically the circuit's rulebook. If S is 1 and R is 0, the output becomes a 1. If R is 1, it resets to 0. If both are 0, it just holds whatever value it already had. But look at that last line. What happens when you tell it to set and reset at the exact same time? You get the forbidden state. You're telling it to do two completely opposite things at once. And this is where the chaos really starts. A user on Reddit put it perfectly. The real problem isn't just being in the forbidden state. It's trying to leave it. When the inputs switch from both being 1 back to both being 0, the two gates start this frantic race to see which one settles first. The output can just bounce back and forth wildly between 1 and 0, completely unstable. Now, of course, engineers saw this problem and tried to fix it. They came up with a more advanced version called the JK flip-flop. It was designed to solve that whole forbidden state issue, but in fixing one problem, it accidentally created a new and honestly even more dramatic kind of race. The idea was actually pretty brilliant. Instead of having that 1-1 input cause an error, the JK flip-flop says, oh, you mean toggle. So it just flips its stored bit to the opposite state. If it was a 0, it becomes a 1. If it was a 1, it becomes a 0. They turned a bug into a feature. Or so they thought. And this, right here, is the climax of our story, the race around condition. See, that new toggle feature had a fatal flaw. If the command to toggle was held for just a tiny fraction of a second too long, the output would toggle, and that new output would feed back to the input and tell it to toggle again, and again, and again, totally out of control. So let's break that down. The clock signal goes high. That's like the starting pistol for the toggle command. The output flips. But here's the catch. The clock is still high. So that new output immediately races back to the start and tells the circuit to flip again. The circuit is literally chasing its own tail, creating this super fast oscillation that makes the final output a total mystery. So how on earth do you stop this frantic race? Well, the answer is one of the most elegant and important solutions in all of digital electronics. It's called the master-slave flip-flop, and it's what makes modern computing possible. The whole concept is just genius in its simplicity. You basically just take two flip-flops and wire them together one after the other. The first one is the master. It listens to the outside world. The second one is the slave, and it only listens to the master. The best way to think about it is like a two-door airlock system. Okay, so on the first part of the clock signal, the outer door of the airlock opens. The master flip-flop takes a look at the inputs and figures out what it's supposed to do. But, and this is the crucial part, the inner door, the one to the slave, stays completely shut. The final output doesn't change a thing. Not yet. Then, on the second part of the clock signal, that outer door slams shut. The master's decision is now locked in place. It can't change. And only then does the inner door to the slave finally open. The slave just calmly copies the stable, locked-in decision from the master. That two-step process completely breaks the feedback loop. The output can no longer race around to the input. Problem solved. And this quote just nails the key idea. The slave is isolated from all that initial action. It only gets the final, settled command from the master once everything is stable and calm. The race is completely prevented before it can even start. Okay, so we've just solved a tiny mystery happening at a nanosecond level inside a microscopic circuit. But let's zoom out, because why does this matter so much? What's the big picture here? So let's just recap what we figured out. We learned that flip-flops are the fundamental building blocks of memory. We saw how uncontrolled timing leads to race conditions, which create total unpredictability. We uncovered the forbidden state in the simple SR latch, the nasty race-around flaw in the JK flip-flop, and finally, the absolutely brilliant master-slave design that brings order to all that chaos. And look, this isn't just some abstract theory. Every single time you save a document, send a text message, or even just watch a video, you are relying on this principle. That 100% reliability we expect, we demand from our digital world, is built on the foundation of these clever solutions to these really fundamental timing problems. And that kind of leaves you with one last thought to chew on. We've built this incredibly stable digital world by taming all the races we know about. But as our technology gets faster, smaller, and more complex, new and even more subtle races are always popping up. The real ongoing challenge for engineers is to stay one step ahead, to make sure our digital world stays predictable in a universe that is anything but.